Hello everyone, and on behalf of the University of Sydney's 2015 National Instruments Robotics Competition team, Conveyance Robotics, my name is Michael and I'll be guiding you through this RC Servo Control tutorial using the LabVIEW development environment and the myRIO hardware. In this tutorial, we'll be trying to accomplish the control of a 3-pin radio control servo from the LabVIEW front panel interface. In doing so, we will be implementing good parallel design strategies that take advantage of LabVIEW's inherent functionality for parallel design. We will be exhibiting some basic LabVIEW functionality such as shift registers, loops, and cues. The hardware for this system is fairly straightforward. It just involves a simple 5-volt 3-pin RC servo powered via a 12-volt cell and a 5-volt regulator. The ground references for the cell, regulator, servo, and myRIO are all connected to provide a common reference to digital ground. The servo is commanded using the PWM output of the myRIO multiplexed to port A. A picture of the hardware demonstration shows the voltage regulator placed in the breadboard with the common ground lines linking all devices and nodes. A peg is used in lieu of a servo horn to demonstrate the movement of the servo in response to the front panel interface. Before we begin the demonstration, we will be reviewing the LabVIEW code. In particular, we'll be looking at the LabVIEW front panel with the controls and indicators that adjust the servo's position, the LabVIEW block diagram, which exhibits the functionality of the program, and the deployment to the myRIO. During the demonstration, we'll be exploiting execution highlighting to show the data flow of the program.
Now in the LabVIEW front interface, we can see both the control knob and the indicator, which shows the position of the control knob. The control knob allows an input between 0 and 180 degrees as an integer, which will be sent to the myRIO. The indicator maps that control knob to the closest integer and just allows us some simple feedback. Going to the back end, we can see that the block diagram is composed of initialization, processing section, and closing. In the initialization section, points of interest are particularly the queue initialization function here, which allows us to initialize a queue that pushes data between the two parallel loops seen in the center. The top loop is tasked with interfacing and reading the front panel, which takes our control input servo position and compares it to previous loops. On a first match with the shift register, we'll see that nothing occurs and nothing is added to the loop, and we implement timing of 125 milliseconds to avoid excessive CPU usage. In the case of the false statement, where the new input has been generated that does not match the previous iteration, the new input is sent to the queue down to the second loop, which is tasked with generating the PWM cycle. The integer value between 0 and 180 is converted to a duty cycle as a percentage of the 50 Hz period and passed into the express VI. The express VI in question allows output on the PWM 0 pin. If we look in the express VI, we will see that the frequency is set at 50 Hz constant, which is a standard for most RC servos, and the duty cycle is set to use input, which is what is being driven in that loop. The connection diagram can be quite useful for pinning out the hardware for applying our LabVIEW in a real application. Upon closing, when we end our simulation, we'll see that the reset myRIO function is called, and the close queue sub-VI is called to free up resources. We've turned on highlight execution and are now pushing to the myRIO. Upon deployment, we will see that the system begins to run. After initialization of the queue, the control input is read for the first time in the top loop, and since no prior input has been found, it does not match the previous loop. This tasks the input of 104 degrees to the queue, which is sent to the second parallel loop and converted to a duty cycle, which is fed into the express VI and out the PWM. We see that as the top loop continues, no change in input has been received, and no additional values are added to the queue. But if we change the input to something else on the front panel and go back to the loop, we will see that a new input is registered on the next iteration. This mismatch causes a new update of the notifier on the queue, which is sent down to update the PWM cycle out. Upon closing, the system is reset to save resources.
We will now see a live demonstration of the hardware with the interaction with the front panel interface. As you can see here, I am beginning the running of the VI, which deploys the program to the myRIO. Upon deployment, we'll start to change the control knob on the front face commanding a position to the servo. It's important to note that every servo is different, and that a command of 180 degrees in software won't translate to a duty cycle command in the servo of exactly 180 degrees. But we can see that the interface is quite responsive thanks to the parallel nature of the program. On behalf of the team, I'd like to thank you for watching our tutorial, and please stay tuned for further updates.